Good morning, Joseph.
Good morning.
Good morning, Miss Ivy.
Morning.
Hey, have you asked me a question I haven't answered yet?
I emailed you one and you told me to use the homework thing.
Yeah, there wasn't something last night.
I'm trying to think. I know there was one time I was trying to do a problem and I wanted to use the step-by-step thing, but it didn't come up. But I don't know, I got through it.
Okay, all right. Sometimes, actually most of the time, I have set that step by step and help me solve this until not to be available until you're reviewing it, because I don't want anybody to try to learn the material just by doing the practice or help me solve this. I think on the word problems, I made it available before you did the problem. You could watch the video, but on the rest of the assignments, I've made them so that you have to attempt it, then you can go to your grade book and review, and as you're reviewing, you can click help me solve this or view example, but not until then.
Well, I remember what problem it was now. It was on a 4.1, and I had an attempt down, and like I ended up getting the right answer, but I couldn't understand why, and it wouldn't let me use the help me solve this before or after my last attempt on it.
Do you remember what problem that was, and do you still need help on it?
Yeah, I have it written down somewhere here.
Okay. Hold on just a second. Let me grab mine. 4.1. All right, what was it?
Okay, it was number 6, y equals, I'll wait till you write it down.
4.1 cosine pi x over 2.
It was in my math lab.
Oh, I'm sorry. No one. Okay, I was looking at my notebook. I'm gonna flip this over. All right, tell me.
Y equals 2x times the square root 4 minus x squared.
And what were we supposed to be doing on that problem?
Finding the derivatives and finding the zeros and the undefined numbers, and then saying which one of those were the maximum and the minima.
Okay, so maybe finding the critical points, and remind me again what the critical points are.
I'm really bad at saying the definition off the top of my head. Like I know what they are, but I'm bad at saying it.
I'm letting you practice because you're a tutor.
Yeah.
Okay, so in your best attempt, and I'll help you out if you need it. What's a critical point in calculus?
Let me think for a second. I've just been thinking of them as points where the derivative is 0 or undefined.
That is half the definition right there, and that's very good. But there's one important stipulation that you're leaving out. Not only does it have to be where the derivative is 0 or undefined, but what's your other condition for being a critical number?
Closed interval or the endpoints?
No.
The function has to be defined.
The function, oh, very, very good. The function has to be defined there. So, for example, if you have a vertical asymptote, then that vertical asymptote, wherever that vertical asymptote is, can't be a critical number because the function's not defined there. Even if the derivative is 0, the function's not defined there, so it can't be a critical point. And that's an important distinction in critical points. So the first thing when I'm asked anything about critical points or maximum or minimum, the first thing I want to pay attention to is what's the domain of this function, because I can't let anything outside the domain I can't call it a critical point. What's the domain of that function?
Anything between -2 and 2, including those numbers.
Correct. You could take the square root of 0 or anything bigger than 0, so x can be anything between -2 and 2. Anything outside that can't be a critical point. Now, to find the critical points, you have to find this derivative, and it would take the product rule. I'm going to think of that 2 as just being outside those brackets and not include it in the first factor. Doesn't matter if you did, it's okay, but if I have a constant, I'm just going to keep it out front. So let's see if you got this derivative. There's the first times the derivative of the second, all of that, plus the second times the derivative of the first. Is that what you got before you cleaned it up, Ivy?
Yeah, I think so.
All right. And before I try to factor anything out, I'm going to clean up all the monomials in this first term. X times a half times -2x would just be -x squared. And this is why we did those simplifying expressions from calculus in pre-calculus, because we need to be able to write that as a single fraction to be able to see what would make it 0 or what would make it undefined. So what did you factor out, Ivy?
I factored out 4 minus x squared to the -1/2.
Right. And what did that leave you inside brackets?
-x squared plus 4 minus x squared.
Right. And I'm going to, even though you don't need parentheses, I'm going to put it in parentheses so that when I check it, I can say this -1/2 plus that 1 is what gave me that +1/2. All right, so simplifying that as much as possible, I have 2 in the numerator. I have square root of 4 minus x squared in the denominator, or I could leave it 4 minus x squared to the 1/2 in the denominator. Combine like terms here, and I have 4 minus 2x squared. Now, that would be okay. You could set that equal to 0, or you could factor another 2 out of the numerator. And have that. So you have your derivative correct?
Yeah.
Okay. Now I'm thinking, what makes that 0 or undefined? What would make it undefined?
The denominator being 0.
Which would mean x being what?
Plus or minus 2.
All right, so if x is plus or minus 2, then that makes expression undefined, but I can only say those are critical numbers if the original function is defined at plus or minus 2. Is the original function defined at plus or minus 2?
Yeah.
Yes, so those are critical numbers. Because the function's defined there, but the derivative is not. Now, what about the derivative's also undefined for, let's say, 3. 3 would make the denominator undefined. So could 3 be a critical number?
No.
Because the original function's not defined there. Again, the definition of critical numbers is the original function has to be defined there, but the derivative is not undefined, or what's the other thing? The derivative.
Oh, you're asking. Sorry.
Yeah. The derivative okay, so is undefined or
say
0.
0.
What makes a fraction 0?
Plus or minus the square root of 2.
Right. So we have 4 critical numbers. Right?
Mm-hmm.
And let's see. If the problem just said find the critical numbers, we're through. If it said find if the critical numbers are max and min, then what do we do?
Make a XY chart and plug them into the original function.
All right, because at this point we were looking for relative max and min, and we said, no, I'm sorry, absolute max or min, and we said absolute max and min can only occur at critical numbers or the endpoints of the interval. And we weren't given a closed interval here. Turns out our domain was a closed interval, but we weren't just looking for critical numbers on a closed interval. So XY chart, and I would put -2, I'm just going to put them in order, smallest to largest, -2, negative square root of 2, positive square root of 2, and positive 2. Now, did you get all those? Oh, another question. Am I looking for the y values for the derivative or the y values for the original function?
The original function.
Right. I already know what the y values for the derivative are. That's what makes the derivative 0 or undefined. I want y values in the original function. So did you get all these y values, Ivy?
Yeah.
For -2, y is what?
0.
0. And for +2, it would be 0 also. What about negative square root of 2 and positive square root of 2?
-4 and 4.
All right. -4 and 4. And I'm just double checking. If I put square root of 2 in place of x squared there, it would just be 2. And that would be square root of 2. I didn't do that very well in my head. 2 square root of 2 times the square root of 4 minus square root of 2 squared would be 2 square root of 2 times, that would just be square root of 2. Yeah, double checking. I knew you were right, but just double checking. Okay, so what does that tell us?
It tells us which points could possibly be the maximum or the minimum.
Not only possibly, but yeah, the lowest one of those y values is the minimum, and the highest one of those y values is the maximum. So this is the absolute min, and this is the absolute max. Now you can either say the absolute max is 4, or you could say the absolute max occurs and then list the ordered pair, square root of 2, comma 4. Is there anything else we were supposed to do there, or is that it?
That's what I got, but the thing that confused me was that they said that -20 is also a maxima and that 20 is a minima.
Okay, then they're talking relative max and relative min. It's not absolute max because 0 isn't higher or isn't lower than -4, but they're relative max and min because the derivative is 0 or undefined. I'm trying to think of, in 4.3 tomorrow, we'll use the first derivative test to say that, but we don't know the first derivative test yet. What did we know in 4.1 that let us say that those are relative max and min?
Would it just be looking at the graph and
yeah,
saying higher than lower?
Yes, it could definitely be looking at the graph. I'm just trying to remember if there was any theorem yet. No, we have a theorem that says if there is a relative max or min at C, then C is a critical number. But up until this point, we would have just had to look at the graph. Just because it's a critical number doesn't mean it's an absolute max or min. So yeah, we would have had to look at the graph up until section 4.3, and then we're going to know a way to say, without looking at the graph, yes, that's an absolute max, or excuse me, relative max or min.
Okay.
Yeah.
Well, thank you.
You're welcome. Okay, so what about 4.2? The two things in 4.2, and one of them's more important than the other. When I say more important, sometimes in math, one theorem is used to prove another theorem, and then you don't really use the original theorem after that. That's kind of how it is with Rolle's theorem. Rolle's theorem can be used to prove the mean value theorem, but there's no other time in calculus that we're going to mention Rolle's theorem. There are other times in calculus we're going to mention mean value theorem. It turns out that at the very beginning of calculus 2, we'll say, hey, remember the mean value theorem for derivatives? Well, there's also a mean value theorem for integrals. So just kind of keep that in your head somewhere. Rolle's theorem just says if you have a function that's continuous on some closed interval, so maybe that, a function that is continuous from A to B, and if f of A equals f of B, then somewhere between A and B, the derivative is going to have to be 0. Now, I wasn't thinking really hard when I drew that graph. Yeah, I'll come back to that one in just a second. Let me say if f of A equals f of B, and the function is continuous on the closed interval and differentiable on the open interval. Now this function is continuous on the closed interval. You can draw all the way from A to B without picking up your pencil. It is differentiable on the open interval, but it's not differentiable on the closed interval because you cannot approach B from the right and you cannot approach A from the left if these are just endpoints. So if a function is continuous on a closed interval, differentiable on an open interval, and f of A is f of B, then there's at least one point between A and B where the derivative is 0. In this second illustration that I drew, how many points are there that the derivative is 0? How do you even know by looking at a graph? Oh, the derivative's going to be 0 right there.
2?
Hmm?
Are there 2 points?
Yes. And how did you identify those? That sounded like Autumn. Was that Autumn?
No, it's Mackenzie.
Ah, Mackenzie. Okay, I'll stop trying to guess voices. How did you know there were 2 points where the derivative is 0?
Because at the top of the little hump, it looks like if you drew a line, a horizontal line, the slope would be 0.
Yeah. If you drew the tangent line, the slope of the tangent line would be 0 at this high point and at that low point. So here there are 2 places where the derivative is 0. Here, there, like I said, I drew that curve before I plotted the 2 points, so it didn't really make the point that I wanted, but it's going to turn out to be important in 4.4. If that graph went up just a little bit, and then went down just a little bit, well, you'd still have 2 points there. That first picture just didn't illustrate what I wanted it to. Don't worry about it. So in some of the problems in 4.1, we're asked to tell whether or not Rolle's theorem applies, and then we're asked to find the points where the conclusion of Rolle's theorem applies, or find the points where the derivative is 0. So those would have been 7 through 30. Do you have any questions from the notes or from any of the odd problems 7 through 30? All right. By the way, before I forget to say it, you probably already noticed already, I extended the homework deadline for 3.7 day 2 and for 4.1. I'm not sure if I made it, I think I made it midnight tomorrow, but you'll see it when you log into My Labs Plus or My Math Lab. So nobody's late on that homework yet. All right, so no questions from Rolle's theorem? Okie doke. Let's talk about the mean value theorem, which is illustrated very well with this picture I just copied from the book. The mean value theorem says if a function is continuous on the closed interval and differentiable on the open interval, in other words, it has the same conditions as Rolle's theorem does, then there exists some number C in the open interval from A to B such that f prime of C is f of B minus f of A over B minus A. And you read that and go, what the heck? What does f prime of C represent? It's the symbol for what? Anybody there?
Slope of the tangent line.
Yes, it's the symbol for the derivative, and the derivative means slope of the tangent line. So this is the slope of the tangent line at C. And what is this?
That whole thing.
Yeah, that whole right-hand side. What is that?
It's just slope formula. Or
It is the slope
yeah.
formula. This is the difference in two y's. This is the difference in two x's. And you can see that better when you're looking at the picture. You have some point A f of A and some point B f of B. The definition of secant line is the line connecting 2 points on the graph. So this secant line connects these 2 points, and the right-hand side of mean value theorem is just the slope between those 2 points. In other words, mean value theorem is guaranteeing us that when these two conditions are met, there is at least one point on the graph where the slope of the tangent line, I left out the word where there, the slope of the tangent line equals the slope of the secant line through the endpoints of that interval. Now what that really means, or what I can relate it to that you'll remember is when we were finding the definition of the derivative. You remember the activity you did with how fast was I going on my way from Dunkin' Donuts to the airport? Somebody say yes, just so I don't feel like I'm talking to myself.
Yes.
Okay.
Yes.
Okay. We said that to find out how fast I was going at the very moment I passed the Monterey exit, we would use intervals that were closer and closer to the Monterey exit, use my speed on either side of the Monterey exit, and at some point we would have the instantaneous speed as I passed that sign. In other words, if my average speed from Dunkin' Donuts to the airport turned out to be 70 miles an hour, if my speed was some continuous function from Dunkin' Donuts all the way to the airport, sometimes I may have been going slower than 70 miles an hour. Sometimes I may have been going more than 70 miles an hour. But if my average is 70 miles an hour, at some point I had to be doing 70 miles an hour. I can't, when I'm driving, I can't jump from 60 miles an hour to 80 miles an hour without going through 70 miles an hour. Did that last sentence make sense?
Yeah.
Mm-hmm.
Okay, that's what the mean value theorem is saying. Somewhere that instantaneous rate of change will be what the average rate of change is. So like we did with Rolle's theorem, we have some problems that say determine if the mean value theorem applies, and if it does, find those values where the slope of the tangent line is the same as the slope of the secant line. Do you need to ask me anything 43 to 48? Or 43 to 45, I guess. 43 and 45. Those, it's easy to do these problems. It may be a little bit harder to understand what the mean value theorem is saying and why it's important. But again, it's just saying you can't go from 60 miles an hour to 80 miles an hour without going through 70 miles an hour, as long as you have a continuous function. I'm through unless somebody has a question from anywhere. All right, let me tell you one other thing. I know that these aren't the best of conditions for us not to be meeting and me there at 7:30 in the morning, whatever, but I think you're getting the same concepts, close to the same quality of instruction, in that you're watching my videos. I'm just not there saying it to you. Y'all don't worry too much about, well, let me just say, don't pre-worry. Don't be freaking out about test 3 yet. I know the related rates problems are difficult. They're difficult for everybody the very first time you see them. And the more of them you do, the better you get at it. I think in Momentum, do I have a page that says extra practice on related rates? Has anybody seen a worksheet like that in Momentum?
I think I glanced over it, but I didn't go directly to it.
Okay, that's the only way to get better at them, just to do a lot of them. So if you do those extra practice problems, and then you just email me and say, hey, I'm working on this problem and here's how I set it up, is that right? Then we'll work one-on-one via email and pictures of your work. We'll practice more of those. And then I have some more of them on the practice test. But I'm never, ever going to put the hardest one on the test. I feel like you need to do homework harder than what's on the test, so that when you get to the test, you go, oh, this is easy compared to the homework. That's my goal. I don't always make that goal, but that's what I'm shooting for. So give me just a little bit of trust that I'm not going to put the hardest one on there, and don't pre-worry. All of you who at some point have been nervous and afraid that you didn't understand the concept well, by the time the test rolled around, you got it. All of y'all have already proven that you're good at math and that you're going to be fine. I'm not worried about you, as long as you keep working hard. All right, well, that's all I have. I'll put this video in Momentum, and there is some 4.1 homework already in my math lab. Not 4.1, 4.2. I've already put 4.2 in my math lab. So y'all catch up on everything you need to by tomorrow. Okie doke.
Artichoke.
Right.
All right, y'all have a good day.
Bye.
Bye-bye.
Bye-bye.